Hello everyone, welcome to the Reliability Insider channel. In reliability engineering, failure rate can mean different things. In this video, we will focus on a very practical question. What percentage of units fail within their first year? Here I will show you how to estimate the 1-year failure probability, avoid a common denominator mistake, and decide when a simple calculation is good enough, and when Weibull analysis is needed. So let's get started. Here the question is, among all the units in field, what fraction fails within 1 year? In order to know that, we need to first look at the lifetime data from the entire population, which includes both the failed parts and the surviving parts. We then fit a lifetime distribution to the data. You may sometimes see lifetime summarized using a simple average, or fitted with a normal distribution. But these approaches may not adequately handle censoring or the shape of typical reliability lifetime data. A commonly used approach is the Weibull distribution. We fit Weibull to estimate its shape parameter, beta, and the scale parameter, eta. And the Weibull PDF, or the probability density function, describes the distribution of failure times, while the Weibull CDF, or cumulative density function, gives the cumulative probability of failure by a given time. For our question, the CDF is what we need. We simply look at the CDF at 1 year. In this example, the number is 50%, meaning the estimated probability that a unit failed within its first year is 50%. Now let's look at the common denominator mistake. Sometimes, the 1-year failure rate is calculated as the number of failures within 1 year divided by the total number of failures. Let's use an example to see why this can be misleading. In the population A here, we have 1,000 units. All the 1,000 units eventually fail, but only 10 failed within 1 year. If you use total failures as the denominator, you will get a failure rate of 10 divided by 1,000, or 1%. And then in the population B, we also have 1,000 units, but only 10 units fail, and all the 10 failures are failed within the first year. With the same calculation method, we get 10 divided by 10, which is 100%. So this matrix makes the population B looks dramatically riskier, 100% versus 1%. But both populations actually have the same 10 early failures out of the total 1,000 units. From a population-based view, that is 1% in both cases. And notice something even more important. Population A could actually have much higher overall failure risk than the population B. After the first year, almost all the units from the population A eventually fail, while 990 units in the population B never fail during the observed period. The problem here is the denominator. Dividing by the total failures only tells what the fraction of the observed failures occur early. It does not tell you the probability that a unit will fail early out of the whole population. So, what shall we do in engineering practice? The key message is simple. Do not estimate the 1-year failure probability using only the failed population. However, as a practical shortcut, we can use the number of 1-year failures divided by the total population at risk. And this simple calculation is often good enough when most units have reached their 1 year in the field, or when exposure is reasonably similar, or censoring before 1 year is limited. And it is especially useful when you just need a quick metric. But when units enter service at different times, when exposure varies significantly, or many units are censored before 1 year, Weibull is a better choice. It accounts for both time and censoring, and it also allows us to estimate the failure probability at different ages, not just at 1 year. So think of this as 3 levels. Using only the failed population can answer the wrong question, and using the whole population is a useful engineering shortcut. And Weibull is preferred when exposure time and censoring need to be considered. And here is one final note. Strictly speaking, failure rate can refer to other reliability concepts, such as hazard rate or Crow-AMSAA failure intensity. Here we have focused specifically on the probability of failure within a given time. And that's it for today. I hope this gives you a more practical way to think about the 1-year failure rate in your engineering work. If you find this useful, please subscribe to the Reliability Insider channel for more practical reliability topics. Thank you for watching, and I will see you next time.